Okay, hi there. We're back for section 2.5 on exponentials. And this is the last section for the first test this spring. So there's 4 parts to this video. First we'll do a little introduction to exponential functions. What are they? How are they different from the power functions that we've seen before? And then we'll move on to stuff that has problems from the book. So moving exponential graphs around, that's this set of problems. And that's very similar to what we did in section 2, I think it was, about moving graphs around. And then solving exponential equations, that's these problems. And then finally compound interest and continuously compounded interest, and that's those problems. So we'll start with an introduction to exponential functions. So in exponential functions is y equals b to the x. B is some positive number, and that's called the base. And this is different from power functions like y equals x squared, because there the base is a variable and the power is a constant. For exponential functions, the base is a constant, but the variable is the power. So the x is up in the exponent, and the base is constant. So here's this 2 standard power functions, y equals 2, exponential functions, sorry, y equals 2 to the x and y equals 3 to the x. So we want to find some stuff out about these. So we'll plot them. We'll make a graph, and we'll start by making a little table. So x's and y's, what are the usual x's and y's we want to deal with? Well, minus 2, minus 1, 0, 1, 2. And what are the numbers we get out? Well, we'll start at the bottom because it's a little bit easier. 2 squared, right? The x goes up in the exponent, so 2 squared, that's 4. 2 to the 1 power, that's 2. 2 to the 0 power, well, anything to the 0 power is 1, right? So for an exponential function, you always get 1 for x equals 0. Now 2 to the minus 1, remember that when back in the appendices, when you have a negative exponent, you put it down on the other side of the fraction. So 2 raised to the minus 1 power is 1/2. 2 raised to the minus 2 power is 1/4. And we can do the same thing with 3. What's 3 to the minus 2? Well, that's 1 over 3 squared, so that's 1/9. 3 to the minus 1, you put the 3 down in the denominator, so that's 1/3. 3 raised to the 0 power is 1. 3 raised to the first power is 3. 3 raised to the second power is 9. Great, and so now we can sort of sketch out a graph of these things. We don't really need too many negative x's because we only get positive numbers out in our range. And remember that our x's, that's our domain. The y's here, things coming out after you've done the calculations, that's our range. So for 2 to the x, well, we'll go 1, 2, minus 1, 1, 2, 3, 4, 5, 6, 7, 8, 9. Because that's how far we have to go for 3. Okay, so for 2 to the x, right, it goes through the point 0, 1. That's this one. And then at 1, it goes through 2. And then at 2, it goes through 1, 2, 3, 4. Right, so it looks more or less like that. At minus 1, the output is 1/2, so that's about there. And at minus 2, the output is 1/4, so that would be about there. So 2 to the x looks something like this. Right? It gets steeper and steeper as you go off to the right for bigger and bigger positive numbers, and it gets closer and closer to 0 as you go out to the left. 3 to the x is the same. We'll do that one in red just to differentiate between the two. So when x equals 2, y equals 9 for 3 to the x. So that's way up here. And then 3 when x equals 1. Like y equals 2 to the x, it goes through 0, 1. And then 1/3, which is a little bit less than 1/4, and 1/9, which is even less. So to the right, now y equals 3 to the x goes up high like that, and then underneath for negative numbers. Okay, so what do we see about our exponential functions here? What can we say about them? One, for negative numbers, right, y gets very small, right? 1/3, 1/9, the next one is 1/27th and 1/81st, etc., etc. As you go up through positive numbers, y gets very big, right? So if y's are getting big, that means you're moving way up. If y's are getting small, close to 0, then it means you're flattening out as you go out to 0. And b to the 0 equals 1, no matter what base you're dealing with. So all exponential graphs go through that point. That's a useful thing to know about these graphs. So, oops, let's not go down too far. So what are these notes we have? Approaches the x-axis to left. It's technically called a horizontal asymptote. It gets closer and closer to 0, but never goes to it. Right? So these curves, as you go out to the left, they get closer and closer and closer to the x-axis, right? Y gets smaller and smaller and smaller and closer to 0. Never actually gets there. Y is always greater than 0. So what does that tell us about domains and ranges? Because that's something we're always interested in. For any exponential function, domain is all reals, and the range is y greater than 0. And that's for functions that look like that, y equals b to the x, where b is any positive number. Okay, so that's the domain and range. Basic facts about exponential functions. Now, there's a particular exponential function that we're very interested in. So here's our familiar functions. Y equals 3 to the x. Oh, this one is y equals 2 to the x in black. In what's that, blue, we have y equals 3 to the x, and then in red we have a new function called y equals e to the x. Let me be a little bit clearer that that's an e to the x. There we go. So e is some number. It's just a number, 2.718 dot 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 dot. It's an irrational number, so that goes on without repeating. But it's just a number. It's between 2 and 3. So the graph of e to the x lies in between the graphs of y equals 3 to the x and y equals 2 to the x. It's a little bit above y equals 2 to the x, a little bit below y equals 3 to the x. Like all exponential functions, it goes out to 0, but never really getting there as you go out to the left. So e to the x, e is just a number, and it behaves, its graph looks like every other exponential function. It's a very useful number. We'll see its connection to interest in section 3.2, but for us it's just a number between 2 and 3. So y equals e to the x, domain, all reals, it's an exponential function, range, y is greater than or equal to 0. Now this is an interesting thing, the range y greater than or equal to 0. What does that mean? It's got no x-intercepts, because to have an x-intercept you have to have y equal to 0. And another way to say the same thing, range is greater than or equal to 0, or not greater than or equal to 0, sorry about that, strictly greater than 0. No x-intercepts. That means the equation e to the x equals 0 has no solutions. Right? So if we try to find the x-intercept of this, we set y equal to 0 and try and solve it, but there is no solution. There's no point on the graph that goes through 0 there. So that's some useful things to know about e to the x. And if we scroll down a little bit further, we get to our next example. What about negative exponents? Y equals 2 to the minus x. So here, this is 2 to the x, right? X equals 1, y equals 2, x equals 2, y equals 4, x equals minus 1, y equals 1/2, x equals minus 2, y equals 1/4. The red curve is y equals 2 to the minus x. And there's a relationship between them, which hopefully you see from the graphs. They're the same graph, just flipped over the y-axis. Right? So y equals 2 to the minus x comes down like this, y equals 2 to the x goes down like that. So why do we get that kind of a thing? Well, y equals 2 to the minus x, what's that? It's 1 over 2 to the x, right? Because it's a negative exponent, kick it down into the denominator. We could also write that as y equals 1/2 to the x power. So, when we're looking at 2 to the minus x, if we set up a little table, y equals 2 to the x, y equals 2 to the minus x, and we plug in our usual suspects for x's. We already know that 2 to the minus 2, let me give myself a tad more space. Two to the minus 2, that's 1 over 4. But if I plug in x equals 2 into this function, what do I get? I get 2 to the minus 2. So that's 1 over, down here, we'll have 1 over 4. 2 to the minus 1, we know that's 1/2, but if I plug in x equals 1 into this function, I get the same thing, 1/2. So for 2 to the minus x, I get, take this number, switch its sign, and then I get the right y-coordinate. Of course, 2 to the 0 is 1. 0 doesn't matter whether you're positive or negative. 2 to the 1 is 2, but 2 to the minus 1, if I plug in minus 1 here, I get 2 to the minus 1, which is 2 to the 1, which is 2. 2 squared is 4. 2 to the minus 2 is 2 squared, so that's 4. So, where y equals 2 to the x is height 4, right, that's here, y equals 2 to the minus x will have the same height, but on the opposite side. So if we have a negative exponent, a base that's bigger than 1 raised to a negative exponent is just flipped over the y-axis. But the range is still y greater than 0, so this equation still has no solutions. Okay, so that's the basics about our exponential functions. And we'll see how this works out in moving graphs around. So there's a bunch of problems with this, just trying to get people to sketch enough graphs of exponential functions so you know what it look like. So, from the graph of y equals e to the x, graph y equals minus 2, e to the x minus 3 plus 4. So we start with the graph of y equals e to the x. And what do we know about any exponential? It goes through the point 0, 1, and it's got a tail 1 unit below that goes out to the left, and it goes up very steeply. That's my x-axis, that's my y-axis. Right? And it goes through a height 1. And it got the tail, and the tail is 1 unit below the y-intercept. So, to graph this, what's the first thing I want to do? Right? First thing to do is move left to right. And there's my x minus 3 in the exponent. So what I've done is before I put the number in, right, before I do any calculations, I have to subtract 3 from my x. So x minus 3, that means I'm moving right 3 units from my x minus 3. So we take our graph, we go right 3 units, height of 1, same picture, goes up that way and flattens out that way. Okay, what's the next thing? Second, scale by minus 2. The minus sign will flip you over the x-axis and the 2 will rescale it. So what do we get here? Since we're going to flip over the x-axis, I'm going to move the x-axis up a little bit, right? Here there's no negative values, so I don't need that. Here there's no positive ones. So 1, 2, 3, because we moved right 3, down 1, 2, because we scaled 2 down, and then this, the tail stays where it is, but the whole thing now is heading down. And then the third thing is, oops, a little too far there. The third thing is the plus 4. Up by plus 4. And so when we're graphing things, it's always left to right, scale, up and down when you want to graph them. That's the order to do these things in. And so now what happens to this point, it goes up 4, which is going to make it at 2. 1, 2, 3. The tail now goes up 4 units as well. Right? It went from 0 up to 4. So the tail is going to be at that height. And there we have it. Y equals minus 2 e to the x minus 3 plus 4. It looks like that. Okay, so in graphing these things, up here, this is going to be left and right, and the negative means right 3 units. Scaling factor out front, up and down outside, and the things to keep track of are where does this point go and where does the tail go. And then you can figure out where the graph goes. Okay. Solving exponential equations. This is pretty straightforward because it really just goes back to doing quadratic equations and stuff. So example 5, so if you look at 29, 30, 31, 32, we want to solve this equation for x. 13 raised to some power equals 13 raised to another power. So whenever I have the same base, that means the powers must be the same. So if 13 to the something equals 13 to something else, I can just look at the powers. We'll see how to deal with different bases in section 2.6, which is about logarithm. So when I have this, we just say, okay, x squared plus 1 equals 7x. Quadratic equation. How to solve quadratic equations? Make sure they're equal to 0 on one side. And you look at that and you think, okay, well, things that multiply together give me 1, add to minus 7. Not much of anything, so let's just go straight to the quadratic formula. Negative b plus or minus the square root of b squared minus 4ac all over 2a. So there's negative b, right? Minus 7 is 7. Minus 7 squared is 49. Minus 4 times a, which is 1, times c, which is 1, so just minus 4 all over 2a. And we can simplify that a little bit. 7 plus or minus square root of 45 all over 2. Make sure your fraction comes all the way out. 45 has got a factor of 9 in it, and that can come out as a 3 if you want. You can just leave it like that. So for these sorts of exponential problems, just set the exponents equal to each other and solve for x. Second type of problems, 35, 36, 37, 38, are like this. Usually we'll want a factor. So what can we take out that's common to each term? Well, 2, 10, 6, those are all divisible by 2, so we can take out a 2. And each term has an e to the minus x. X squared, x, I can't factor an x out because there's no x in that. But I can factor out a 2e to the minus x. And what's left behind? Well, if I take 2e to the minus x out of here, I've got an x squared. If I take a 2e to the minus x out of here, the e to the minus x comes out. 10 divided by 2, that's a minus 5x. And if I take a 2e to the minus x out of this last term, the e to the minus x comes out. Taking 2 out of 6 leaves me with a 3. Ooh, I didn't want that. Shoot. I think I want 12 here instead. So we'll make that 12 so that I get a 6 here, because I want this to factor nicely. So this does factor nicely now that I've changed it a little bit. And when we finish our factorization, we get x minus 3 times x minus 2 equals 0. So, having done factoring, why do we like doing factoring? Well, we know if we have a bunch of things multiplied to give you 0, that means one of them's got to be 0. So now we can solve. So, either 2e to the minus x equals 0, or x minus 3 equals 0, or x minus 2 equals 0. We know that e to the minus x equals 0. There's no solution for that. E to the minus x is always a positive number. The range of an exponential function is always positive. So there's no way, there's no x-intercept, so there's no way that this can be equal to 0. So there's no solution there. Here, well, x minus 3, you can solve that for x equals 3. And here you can solve this for x equals 2. And so what's the solution to our equation? X equals 3 or x equals 2 is the solution. So these kinds of problems, right, you factor them. And remember that exponential functions are never equal to 0. Right? And so if that's one of your factor, you don't get any solutions from that one. You just get solutions from these two, 3 and 2. Okay. And now our last example, compound interest and continuously compounded interest. Here we are. These are two formulas that you'll have to memorize by the second test, not for the first test. You'll be given these on the first test. Right? One is the compound interest formula, A equals P, 1 plus R of RAM to the MT. One is the continuously compounded interest formula, A equals PE to the RT. We'll see much more of these in section 3.1 and 3.2. We're introducing them here because these are interest formulas. They're how much money you have, right? And so this A, is how much money that is in your account at time t in the future. P is the principal, or the amount that you invested at time t equals 0. So that's P here and here. R is the interest rate. R is always in decimals. T is the time. It's always in years. M is the number of compounding periods per year that shows up in two places in the compound interest formula. Why we're interested in compound interest, or why we're interested in interest formulas in the exponential section? Time always is in the exponent when we're compounding interest, and so we need to know how exponential functions work if we're going to be dealing with them in finance. So, great. So, $3,000, here's an example, $3,000 invested at 2.5 compounded continuously. That means I want the continuously compounded interest formula. How much is in the account in 54 months? So how do we do this problem? Right? Compounded continuously means continuously compounded interest formula. So A equals PE to the RT. What do I need to know? I need to know what are my variables. A, P, R, and T. And the way these problems work, and this will be all through chapter 3, is there's 4 variables in this particular formula. They'll give you 3 of them, and you have to figure out the 4th. So $3,000 is invested. That's the principal. 2.5%, that's my interest rate. And so we need that in decimals, 0.025. And 54 months, that's time, but I need 54 months in years, right? Time always has to be in years. So 54 months, it's 48 months plus 6 months, or 4.5 years. Remember, time always has to be in years. And then this is what I want to know. How much is in the account, the amount, in 4.5 years? So you just plug everything in. A equals 3,000. E raised to the 0.025 times 4.5. There should be a button on your calculator for E. And if you calculate this out, you get 3357.22. Then we round that to the nearest, that's supposed to be a dollar sign, don't know what the heck that was. You round that to the nearest cent. E, remember, here is just a number. It's not a variable. It's 2.7 something, right? And your calculator knows what it is. So, you've got the formula, you plug in all the variables, look for the one that you don't know. So, last example for this section. A bank offers a saving account with 2% interest compounded monthly. You want to have $1,000 in 3 years. How much do you have to invest now? So, compounded for monthly or compounded daily or compounded weekly, whatever. See that phrase? That means use the compound interest formula. And what are all these letters? Well, we have 5 of them. P, the principal, R, the interest rate, M, number of times compounded a year, and T, time in years. So, saving account with 2% interest, so convert that to a decimal. That's my R. Compounded monthly, that's 12 times a year. And that's what M is. It's the number of times you're compounded per year, so 12 times a year is monthly. If it was daily, it would be 365. You want to have $1,000 in 3 years, so time is 3,000. You want the $1,000 in the future, so that's the amount in the future. The question is, what is the principal? How much do you have to invest now? So, again, you know everything here except for one of the variables. You don't know what P is. So if we plug everything in, you get 1,000 equals P, 1 plus 0.02 divided by 12, so there's a rate divided by number of times compounded, times 12 times 3, because it's 12 times a year for 3 years, so 36 compounding periods. If you multiply this out, this thing on the right becomes 1.061 ... That's what this whole part is, and then divide by that to get P equal to 941.81, rounded to the nearest cent. Okay, so a lot of Chapter 3 will be dealing with financial formulas, like those two, like some others. So exponential functions are useful. You can see one of the things that we'll be interested in, though, is from these formulas. Let's go up a little bit. Here we go. If you put a certain amount in and you want a certain amount later, right? So suppose I put $1,000 in and I want to wait until I get $7,000. How long was that? Well, that means I have to figure out what this t is. And so one question that we want to talk about, and that'll be for this on this material for the second test, though, is how do you get the x variable down out of the exponent? That'll be logarithms. So key facts about exponentials. If we go back up to the top, here we go. To the left, it approaches x-axis. Exponential functions are always positive, right? And so when you're trying to solve an equation, they'll never be equal to 0. They